Okay, so as we can see, like so for E11 it holds. So what about E12? Can you show that E22 times this thing is 0, that's for sure. But can you show that E kappa lambda T kappa 2 T lambda 2 is also 0? Can you show that?
Yes.
So I think I need not to do that, because I think you can do it by yourself. It's the same thing. So let's do for another one which is non-trivial. So let's do for this 1-2 case, E12 determinant of T. So what should you get? What do you expect to get?
Minus.
No, I want E12. Yes, E12 determinant of T. What do you expect?
AB
So
minus.
Determinant.
Yes, it's positive 1. E12 is positive 1. Determinant is AD minus BC, right?
AB yes. AD minus BC.
AD minus BC. Great. So now let's check for this side. So all we need to do this. So if you evaluate in similar manner, so I'm not going to write sum, like sum over 1. I'll just write down the non-trivial sum. So first non-trivial one would be like E12 T11 T22 minus sorry, not minus, plus E21 T21 T12. So E12 is 1. What is T11 and T22?
A and D.
A and D, right?
I can see it from the left side.
And here it's minus 1 times T21. What's that?
B C.
It's B times C, which is AD minus BC, right?
Yes.
And it holds. So are we convinced enough that it holds this relation? The relation I wrote here, it's true. Are we convinced enough? So basically it's just saying two things, that it goes like P to the power T to the power P, and it's completely antisymmetric in terms of any two indices. So by saying that, that's already we have already proved this statement. But I just wanted to convince everyone. Okay.
I'm not sure that the two properties is convincing enough. How do they prove that?
Okay, so so to define determinant, like you had some like expansion for T, right? Like determinant of T.
Yeah.
So for a P by P matrix, you can always write the determinant. So that that thing has a specific structure. We are looking for that structure only.
That means the properties.
In other words, yes, those are the properties. These two properties.
Okay.
Can you construct any other thing except for determinant that goes like that has these few properties, like these two properties particularly?
We can't say that we can't construct. Maybe we don't know yet.
Okay.
I mean, yeah, we got the properties.
Yeah,
We wanted that.
hard to convince someone from this just these two statements. It's better to show some example, then they'll get it.
I mean, we wanted the properties, isn't it?
No. We wanted to prove this relation, that this is true.
And what is the definition of determinant generally?
Generally, we know how to do it. We just do the what's it called, cofactor expansion, and add those things up, right?
Okay.
We know how to do like how to take determinant for 3 by 3, 4 by 4 matrices, right? So yeah, that relation actually can be generalized in terms of this E. That's actually I have written. So you could say, equivalently, you could say this is the definition of determinant. This
Okay.
is how we define determinant. You could say that as well.
Yeah.
And then convince people this is the usual definition, just written
Can I
fancy
say
in a,
that in this way, that if something has two properties that we proved, this relation will hold?
sorry?
Conversely, if something has two properties, that the determinant is proportional to t to the power p, and the other one is we got two properties, isn't it?
Yes.
If
Yes.
something has that two properties, that relation will hold. So determinant has those properties, so that relation will hold for determinant. Yeah, I'm
Yes.
convinced.
Or more simply, like you could say that this is the definition of my determinant. You could say that as well.
Okay.
Remember, like we do not have that much elementary definition, that we always actually we learned how did we learn taking determinant? How did we learn it? We saw some example for 2 by 2, 3 by 3, and like that we got an idea, okay, how to do it.
Yeah, there's a
Right?
pattern.
That's not the definition. We just know
So
how to do it.
yeah, so what's the definition then?
This is the definition, and we can use cofactor or yeah.
So yeah, you could go the other way. You could say this is my definition, and now you show that okay, whatever we learned from earlier cases, like in childhood, that actually uh, like that thing is covered as well. This
Yes.
is my general definition. You could say that. Okay. So we have a relation among determinant and component of a matrix. Now, how we are going to use that? That's the question. So let's take a 5-minute break, and we'll come back after this break, and we'll talk more about it. Why it's important? That's also a big question. Why taking determinant is important here even. During this break, if you have any question, you can ask as well. These few classes, like exterior calculus class, is actually algebraically challenging. But when you have the algebra, it's not that difficult. Constructing the algebra is the hardest part.
Bhai, I have a question about that permutation symbol.
Yes.
That it is not the tensor component.
Mhm.
So we could expand our tensor in terms of it. In one case, we could
Yes.
expand it,
Mhm.
but it's not tensor component. Now, tensor component, we found tensor component, or we find tensor component by piercing with
No, no, no.
the
A tensor component is a component of a tensor.
yeah
Hmm?
uh,
Here, actually,
yeah.
we before finding the component of something, we define the value of E. That's the problem. We forcefully define some value.
But how could then we could how could we expand in terms of it? I mean, we could expand that tensor in terms of its components, and we can expand that tensor in terms of the commutation symbol. Why can we do that?
So it's a special case where it matches, where the component of that specific tensor matches with this definition.
That means it's just a coincidence.
Yes, it's just one case that matches. When you change the coordinate, that matching is
It
gone.
doesn't hold. Yeah.
So whenever you define something forcefully like this, that this has this value, you should be careful about it. It might not be a tensor, but when you have a tensor set some t and you expanded it in terms of, so then the components are purely your tensor components.
Can it be tensor ever? I mean, this type of forceful definition. Can
Yes,
it
yes, yes, yes.
produce?
There is at least we know one case. We know at least one case where this thing, this Kronecker delta, say mu1, 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 mu2 up to mu p, mu1, mu2 up to mu p. This arbitrary thing, arbitrarily defined object, these are tensor components always.
Yes.
These are
This takes like
Tensor.
in a forceful manner.
also like numbers.
Yes, yes, these are numbers at
It's
plus
not
one, minus one, zero.
tensor.
Hmm?
So how can it respond in coordinate transformation?
So yes, it change
They
like
they
under
converge.
Fourier transformation, it changes such a way that it remains same.
Yes.
We'll see actually,
We'll
we'll
see
see.
that.
Is not it mixed tensor?
Sorry?
A mixed tensor is not it a mixed tensor?
Yes, it's a mixed like mixed tensor in terms of what? Tensors, the way we are dealing with here, these are always mixed. Like you mean upper indices and lower indices, right?
Yes.
So yes, these are in general, everything is mixed tensor. So there will be special cases only. So that's not the point. This has a specific name. These are called numerical tensor. That means a tensor that whose components are always fixed numbers.
Yes. We can prove it actually.
Yes, we'll prove it. Okay, so I think the break is over. So let's continue our journey. Let's clean the whiteboard and then. Okay, so let's write it down again. It's going to be useful, so it's better to write in multiple times. So mu1, mu2 up to mu p. T, when T has written in terms of two lower indices, this thing has a determinant equals to, or actually let's not make it so complicated. Just write like this. We'll understand that T has a representation of lower indices. So we write it usually like this. Mu E mu1, mu2 up to mu p. T what? Mu how did I write it? Actually I forgot. Which one I wrote first?
Uh,
New one.
mu1 that's how I write
Yeah.
mu1 mu1. Okay, t mu2 t mu p like that. Okay, so these for like lower indices. So what do you do? The same thing for upper indices. Like if you want to take determinant that has two upper indices in its representation, how should you write it?
Just switching
Yeah,
from lower.
basically these are the same thing, right? E with upper and lower indices are same thing by definition. So it doesn't matter what you're using. I'm just we were just trying to make this like summation convention consistent, that's all. So it doesn't really matter. You could actually use upper index here as well, doesn't matter, but that would make the like Einstein summation convention inconsistent. So that's why we actually chose to write a different, like write in a specific way. That's all. Okay, so we are going to write like this. So here the sum, like t, I want to write like this: t mu1 mu1, right? As it's like the upper indices.
Yes.
So to make this summation convention consistent, I want to use e with lower indices here, right? So also I should use e with upper indices here. Is that clear to everyone?
Yeah.
What about t has one upper index, one lower index? Like this.
Then we will change permutation symbol as well.
What?
We will change permutation symbol likewise.
Let's write this part first. So it's probably going to be like this: mu1 t mu2 like that. So this e actually it sums over the second index, so we want to write like this.
Yes.
And these are upper indices, so I want my last, like the first e, to be all upper indices, like that. So I believe you get the idea. It's just
Yeah.
way we are writing. We are writing the same thing over and over again. That's all. Okay. So now we have to deal with a specific kind of matrix that we are actually interested in. That's going to be really helpful. So that is the Jacobian of something. Jacobian of a transformation. So say you had your coordinate x mu, and you go to a new coordinate set that is x mu prime.
Yes.
So under this transformation, you could write a matrix out of it with two index. So like this: delta x mu prime by delta x mu, like that, with two indices. So one is upper index, so usually we can write like this: j mu prime mu. Or in a more verbose way, we could write like this: j mu prime, which is basically not new prime, which is new, which is basically x prime by x. Here we actually mean like we are going from x coordinate to x prime coordinate. So x prime is the new one, the x is the old one. So okay, this is again a matrix. That's all, right? It's again a matrix.
Yes.
as it is a matrix, it should have a determinant as well.
Yeah.
So determinant of J, usually we'll write just J or like this, or you could use the double bar, but this is going to be my usual notation for Jacobian matrix, Jacobian determinant. Jacobian determinant, but okay, we need to be precise about this thing as well. Okay, so usually I'm going to write like that. So here let's write down the component. So components are like this: delta x mu prime 1 by delta x nu 1, delta x mu prime 2 by delta x nu 2, up to, it depends on how many coordinates actually you are taking. So if you are taking you are talking about a dimension of n, then you'll have n number of coordinates that's going under transformations, right? So the specific Jacobian would have a, like Jacobian matrix would have a specific dimension. That's what I am saying. So in n-dimensional space, you'll have n number of coordinate x and n number of coordinate x prime. So taking this derivative, you'll have a n by n matrix, remember. So if you have an n-dimensional system that has a Jacobian n by n, Jacobian of n by n dimension, n by n Jacobian, right? So I'll need in here, I'm going to write like the component of that thing n times, so like that. And see which epsilon should I use here.
Epsilon with lower indices.
Epsilon with, you could do that actually, it doesn't matter much. So I'm considering this thing as the later coordinate, this, the upper one is the first one. So I prefer to use this one.
Yes.
Though it doesn't matter. Oh, sorry, not P, it's up to N, right? So here I need to write what?
It's also upper, I think.
It's also upper, yes. So our Jacobian determinant has this relation. Just remember that this is going to be useful. Where? Let's see. Okay. Let's say you are in n-dimensional space and you have n number of coordinates. You are in n-dimensional space. Just remember this thing. So now in n dimension, you could have say you have your coordinates like x1, x2 up to xn. You go through a transformation. You are trying to make a coordinate transformation, that is x1 prime, x2 prime up to xn prime, like that. Now my question is how this object dx1 prime wedge dx2 prime wedge up to dxn prime is related. So here should be something to the old coordinate, that is dx1 dx mu1 wedge dx mu2, like that, dx mu1. In other word, we are actually trying to make a we call it coordinate volume. There is a reason we call it coordinate volume. So coordinate, we are trying to make a transformation of coordinate volume. Let's see what happens.
Okay.
Okay, so we can write just dx mu prime in terms of the older coordinate. So that would be like delta x mu prime by delta x nu dx nu. Is that correct?
Yes.
If it's correct, then this thing should be correct as well, that dx1 prime with dx2 prime wedge up to dxn prime equals to, so we are writing the expansion of the first term, which is delta x1 prime by delta x nu 1 dx nu 1. Then expanding the second one will be delta x2 prime by delta x nu 2 dx nu 2, where dx like nu 1 nu 2, those are different indices, up to like that delta x n prime by delta x nu n dx nu n. We can do that.
Yes.
Okay, so now this part, these are the just components, right? Like just numbers, not components. These are just numbers. We can write like this: delta x1 prime by delta x nu 1, delta x2 prime by delta x nu 2, up to delta x n prime by delta x nu n, right?
Yes.
So then dx nu 1 with dx nu 2 wedge up to dx nu n. So now we have achieved our goal to writing the n form in n-dimensional space in terms of newer coordinate, right? Like this is the relation between older and newer coordinate. Same thing, written in terms of older and newer coordinate.
Yes.
So, but we knew that so the Jacobian is actually related by this relation. Can we introduce it here? Can we see a pattern, like see
Yes.
something that's similar?
Yeah.
Which part is similar?
When we defined the Jacobian determinant of Jacobian matrix, the last part, actually without the permutation symbol, or saying
Without the permutation symbol. So basically, this part is like proportional to n dimension, like Jacobian matrix to the power n. So that's kind of closer to the determinant, right?
yes.
So only thing we are missing here is like if we had this thing and that thing somewhere, then we would be able to write in terms of this. So how do I introduce that over
I
there?
can multiply both sides by permutation symbol.
Okay, one thing is for sure, that is we have x1 x2 up to xn. So if you switch any two adjacent indices, it gives you minus sign, right?
Yes.
Which is basically this antisymmetric structure of E as well, permutation symbol as well. So we could write the same thing, because we already actually seen this. So this stuff can be written as 1 over n factorial E 1 prime 2 prime up to n prime oops. I want to write like this. This can be written as 1 over n factorial mu prime, mu 1 prime, mu 2 prime up to mu n prime, then dx mu 1 prime wedge dx mu 2 prime wedge dx mu n prime. Do you agree with that? We already saw
Yes.
some version of this in 2 dimension, remember?
Yes.
So when you have purely in terms of wedge product, like your d of coordinates in terms of wedge product, then you can write like this. So in one part we have already introduced. We need to introduce the similar thing in other parts as well, on the other side. So what do we do that? How do we do that? Yes. I think we need a little bit more thing to define before doing that. Okay, just pause it over here. We are going to use that, like we are going to derive that, but I think it's better to derive define something else that's going to be helpful here. So this is the thing actually we should define before proving this thing. So what happens when you multiply these two things? So E mu1 mu2 up to mu n, say, then E mu1 mu2 up to mu n. What do you get? Like, what are the possible values of this product? What are the possible values of this product?
+1 -1 0.
Yes, +1 -1 0. Why?
Because for every possible value, we can't get any other things from this.
Yes,
So
you cannot get any other thing. So you are just multiplying either by 0 or +1 or -1. So at max you can get these three things, right?
Yeah.
yeah.
So tell me, when do you get 0?
When repetition happens, any of this permutation symbol.
Okay, what else? Okay, I think 0 case is the hardest one. So let's just tell me, when do you get +1 out of this whole thing?
When they both will give uh, one.
Both odd or both even.
Yes, both
Yes.
or both even.
Both have even permutation in indices, and or both have odd permutation in indices, right? So either sorry, like when both are either
Even.
odd or even, right?
Yes.
So if both of them give you plus sign, then you'll get plus, or if both of them give you minus sign, then you get minus. So when do you get minus?
One even and one odd.
One even and one odd. And any other situation, you get 0, right?
Yes.
Okay, so let's explore this a little bit more, because these properties, actually we have defined something that has these properties. Okay, so how do we use that? So when both are even, like say mu1 is just 1 2 3 like that up to n, and mu2 are like mu n, like mu are also like 1 2 up to n, so then are both even, right? That gives you +1. Now if you have one odd permutation, say here 2 1, or actually no, let's finish the even case first. So this thing, so now say you have this combination, this particular combination, so 1 2 okay, 1 2 3 4, say I have like 7 dimension or 8 dimension, so that would be overkill though. 6 dimension, let's say. I'm talking about with 6 indices. So first one have these possibilities, like first one is fixed. The second one, if those are like 1 2 3 4 5 6, if the second one is also like that, then it gives you +1. So which situation do you get, which more situation do you get positive if these are fixed? So you just change this thing. So what are more possible situations? So if you have like the lower one as 5 4, do you get +1 or -1?
-1.
You get -1, obviously. If you have like also this 1 3 2 5 4 6, do you get
Now
+1?
1.
You
1.
get a +1, right?
Yes.
Okay, just to understand this thing, so if you can make the combination in lower indices such that that matches with upper with even number of combination, even number of switching permutation, then you get a plus sign. Is that a statement correct?
Yes.
You get what I'm saying, everyone? See, here we can actually, with two switching, we can actually do that. So switch, one switch you do, you change these two, another switch you change these two. So this is the thing we call it, like if the lower indices are even in the upper indices, then it's +1. So instead of writing like when both are either odd or even, we just need to have this thing, that one set is even in other. So you can make this set switching even number of times this set, and if you can make this set by odd number of switching in this set, then it's
-1.
a -1. So one set is odd in another. And any other cases, they will give you 0. So there could be cases when number of indices they do not match, like here we have 6 dimensions, so we cannot have like more or less. So if we were in 8 dimension, we could have like more indices, right? Like this could be possible. Like in 8 dimension, 1 2 3 4 5 6 is possible. 1 2 3 4 5 6 is possible, but here this thing like 1 2 3 6 7 8, that thing is possible. So if you have this kind of case, that's 0 as well, because the first one, you cannot make the first one by changing the lower one. So this thing has a special name. We call it this Kronecker delta. That's actually generalization of Kronecker delta. It's written as mu1, mu2 up to mu1, mu2 up to mu1. So by definition of Kronecker delta, this is this, that E mu1, mu2 up to mu1, E mu1, mu2 up to mu1 equals to Kronecker delta upper set mu1, mu2 up to mu1, mu1, mu2 up to mu1. This is the even definition of Kronecker delta, which can give you +1, -1, 0, depending on the evenness of these two sets. If the upper set is even in the lower one, then it gives you positive. If it's odd, it gives you negative. And any other cases that includes that the sets do not match, that also possible, it gives you 0. That's the definition. Hello.
Yes.
Okay. Any question regarding this particular thing, or you are convinced that okay, we can do that? The place is too silent today.
It's just a definition, isn't it?
Yeah, it's definition, that's true, but these other cases, this needs to be explored, right?
Yeah, they were okay, I think, for me.
At least we need to see some example. That's what I believe.
Okay.
Okay, let's check this out. So in three dimension, like you have E with two indices. So the possible E can be like this: E12, E23, and E31. These are the independent positive one. Then E21, E32, E what? 13. These are the positive possible negative one. Now what happens to like this E23, but E I think I made a mistake. Mistake is this relation is true for like when dimension of the thing matches with the number of indices actually. So for 2-dimension this will hold, or 3-dimension with 3 indices will hold. So I think I made a mistake. Okay. Yeah, the dimension, like the number of indices should match the number of dimensions. So yeah, so let's do it in 2-dimension with 2 index, not 3. So the possible things are like E12 and E21. So Kronecker delta with 4 indices can have like 1 2 1 2. That's one possibility. Another is Kronecker delta 2 1, Kronecker delta 1 2. Another is the opposite, 1 2 2 1, and another possibility is just 2 1 2 1, like this. So by definition of Kronecker delta, this thing is positive 1, because if without switching things, you can actually see that this set is this set. So this thing becomes this if you switch just one of the sets. So that gives you -1, this also -1, this also, this is +1. So this is one side. In another side, like you can easily see, like E12 times E12 is basically +1, and E21 times E12 is -1, and so on. So you can see that, right? In 2D, it's if they have 2 indices in 2D, then it's true. Also, same thing is like if they have yeah, okay. So I think we can proceed with that, with this definition. So sorry, I made a mistake. Like it cannot be arbitrary. Like the number of indices here, like to have this definition of Kronecker delta, like to define this thing but this way, actually we can define Kronecker delta in many other ways as well. So basic definition is like if this upper set is positive, even in the lower one, that's positive, and if odd, then negative, then any other cases, that's 0. And this relation particularly that holds in when the dimension is n, like space has n dimension, that manifold you're talking about. Okay. Then we can use this thing as well over the expression we are dealing with here. Okay, to introduce we can introduce a set of Kronecker delta like this: delta x1 prime by delta x nu 1, delta x2 prime by delta x nu 2, up to delta x nu 1 nu prime by delta x nu n times Kronecker delta summed over nu 1 nu 2 up to nu n, then say lambda 1 lambda 2 up to lambda n, dx lambda 1 wedge dx lambda 2 wedge up to dx lambda n. We can do that, right? Using the definition of Kronecker delta, this extended version of Kronecker delta. Hello. Hello.
Yes.
Should there be
Uh,
1 by n factorial type thing?
did I miss something? You mean? No, I think that's the correct expression. Okay, actually, if we are not confident about the factorial part, we can actually derive the other. We can first derive the other thing as well. So that is, instead of doing like introducing Kronecker delta here, we could actually with using the very definition of determinant, we could actually multiply on both sides by same e. That would be helpful as well. So that will like vanish from E1 in one side and introduce in another. So okay, actually let's start with this thing. We'll substitute it back. So as we had like E mu1 mu2 up to mu(n), so with prime indices, equals multiplied by determinant of this equals to E mu1 mu2 up to mu(n). Then what was here? Delta x mu1 prime by delta x mu1 up to delta x mu(n) prime by delta x mu(n). So now actually introducing instead of introducing Kronecker delta here, we just multiply both sides by same e. Same e but with lower indices. So if we multiply both sides by this e mu1 prime mu2 prime up to mu(n) prime, that will give you just multiply on the other side e what did I multiply? Mu1 prime to prime up to mu(n) prime, like that. Okay, yes. This is what I want actually. Okay, so now as you can see, these indices are all summed. So this is nothing but Kronecker delta mu1 prime mu2 prime up to mu(n) prime, mu1 prime mu2 prime up to mu(n) prime times j, this thing, equals to this right hand side. So now our question is, what is this? What's the result of this thing? That's we need to actually calculate.
1.
Is this 1 or something else?
It depends. Okay.
So remember, mu indices are being summed over. Mu indices are being summed over.
Then n.
Almost. You are missing still something. Okay. Okay. Let's see what happens in 2 dimension. That will give us more confidence. So or 1 dimension. So 1 dimension, how many possibilities do you have? Just one possibility,
1
right?
0.
No, not 1 0. It's just 1 1. This is basically
Sorry.
plus 1. That's
Yeah.
1. Then for 2D, if you have some, then you could have like this, 1 1 1. Sorry, not 1 1. It's 1 2 1 2 plus Kronecker delta 2 1 2 1. These are the 2 possible combinations, right?
Yeah.
When the first thing has to match with, like, in the first index in the upper set has to match with the first index in the lower set. So that's the only combination. So what's the result?
2.
It's 2. So what happens when this thing in 3 dimension? So one possibility is 1 2 3 1 2 3 plus, then Kronecker delta 2 3 1 2 3 1 plus Kronecker delta 3 1 2 3 1 2 plus Kronecker delta 2 1 3 2 1 3 plus Kronecker delta 3 2 1 3 2 1 plus Kronecker delta 1 3 2
So
1
n
3.
factorial. This is 3 factorial.
Yes, this is 6. So if you construct more and more, you'll see this is basically n factorial. So if you have summed over n indices, so like this, mu1 prime, mu2 prime, up to mu n prime, then mu1 prime, mu2 prime, up to mu n prime, it gives you n factorial. Actually, we should derive a few more things as well. Or no, let's postpone it for later, because Kronecker delta can have actually in 4 dimension you could have Kronecker delta with 3 indices. You could have that. So that's a situation where actually you need to know the sum. So we'll see that, actually we'll see that later. So for now it's enough. It's enough to know that this part is just n factorial. So what we have seen is n factorial times, if you take determinant of j, it gives you on the other side, it gives you like epsilon nu1 nu2 up to nu n, epsilon mu1 mu1 prime mu2 prime up to mu n prime, then delta x mu1 prime by delta x mu1 delta x mu2 prime delta x mu2 up to delta x mu n prime by delta x mu n, like that.
Yes.
We are sure about this result, so we can divide this both side by n factorial as well. So if you divide, no, for now just leave it over there. So what thing we are calculating is, we are looking into this expression, actually these two expression. Oops. Let's actually zoom out, then we can see the whole board in one. So we were actually talking about this expression, right? This side equals to this side, or actually I need not to worry about that. Actually the upper equation is enough. We were talking about this thing, right, when we paused for a while and went to do something else. So what we can do, we can multiply both sides by similar manner e with contracted index, right?
Yes.
Okay, so this side actually, do this part first. So we have 1 over n factorial, then e mu1 prime mu2 prime up to mu n prime Then we have like dx mu1, dx mu2 up to dx mu n. So my statement is, we can write it as E mm, actually I had that earlier. Or do I want to go backward? Okay, so the expression I have written is actually not most general expression I want. So as you can see, we started with dx1 prime, dx2 prime, like that. We started with this thing. So if I want to write, instead of that, I want to write dx mu1 prime wedge dx mu2 prime up to wedge dx n prime, mu n prime. What would be on the other side? What would be the expression here? What changes do we need to make?
Multiplying.
No. See, when we had dx1 prime wedge dx2 prime up to wedge dxn prime, we had delta x1 prime by delta x nu 1. So the index over here appears index over there, right?
Yes.
So if we start with dx mu1 prime, dx mu2 prime, we should have delta x mu1 prime by delta x nu 1. Like that.
Okay.
Actually, it's a generalization of this statement with arbitrary index, right?
Yeah.
Okay, so where was I? Dx mu n prime by delta x nu n, then dx nu 1 with dx nu 2 wedge up to dx nu n. Okay. To find the structure of Jacobian, what I want to do is, instead of writing here nu 1, nu 2, nu n, I want to write instead this side, right hand side, I want to write dx 1 wedge dx 2 wedge up to dxn. That's what I want to write. What should I do? Can you tell me? I want to write this thing as like this part as this part.
So
So
it is.
let's see. Does this thing suffice? Like this whole part, my state, my what's called proposition is that this thing is equal to that thing.
Yeah, I think it's correct.
Yes.
How?
We need to multiply a permutation, I mean E, in that relation.
Which relation?
Relation. I mean dx. I mean
So
dx1 with dx2 with dxn is equal to 1 by n factorial E mu1 mu2 mu1 mu2. We have this type of relation, isn't it?
okay. So basically, when you can have actually a specific kind of uh, index, like index structure, like dx1 with dx2 with dx3 up to dxn, for the case when nu1 has a value 1, nu2 has a value 2, and so on, right?
Yeah.
So that's one case. So now another thing is when you switch this term with that term, it gives you a minus sign. So in other words, if you switch those two indices, nu1 and nu2, that gives you a minus sign. So that sign is handled by this part, and the first term, like that, when nu1 up to nu-n is just 1 to 3 up to n, that is this part. Actually, I can show an example, then it will clarify, I believe. So let's talk in 3 dimension. So in 3 dimension, oops. In 3 dimension, that expression, that this expression in generally, it's dx mu wedge dx nu wedge dx lambda, right? 3 dimension, we have three things to multiply with. In 3 dimension we are talking about. Okay, so now how many possible combination you could have for mu nu lambda? One combination is mu nu lambda is just 1 2 3. That's one combination. In that case, you could have like dx 1 with dx2 with dx3. That's one combination. Then you could have mu nu lambda equals to say 231. 231. That's another combination. So when you have mu nu lambda equals to 231, you can, it's basically dx2 with dx3 with dx1, right? Now what we are trying to do is to write this thing as the upper one. So if you switch these two terms, it gives you minus dx2 with dx1 with dx3, right? Now if you switch these two terms again, it will give you another minus sign, and finally you end up having dx1 with dx2 with dx3. So you see, this thing is nothing but the above one.
Yes.
So these are two examples of even combination. What about odd combination? So let's say mu you have like 3 to 1. For 3 to 1, so you have dx3 with dx2 with dx1, right? So this thing we want to write in terms of the first one. So which thing should we need to switch? If we switch 2 and 1, so switch these two things once, that gives you a minus sign. Then you have like negative dx3 with dx1 with dx2, right? switch these two things again, that gives you positive dx1 wedge dx3 wedge dx2. Switch again these two things.